So last lecture we looked at the IV characteristics of a MOSFET for a very simple model and for a long channel, so that the physics of the MOSFET was simple. This lecture will look at what are called as second order effects, which affect the behavior of the MOSFETs specifically for short channel transistors. Okay, so we again look at the ID versus VG. So we had seen this plot last time. This red one is the long channel IDVG characteristic, and as we had seen, it is a straight line. It varies linearly, and we had seen that the actual bends over at higher currents because of the series resistance of the source and drain regions. Now let us look at this near threshold behavior of the current. So this is an expanded version of the same IDVG. So the VG is going only up to 0.66 volts, and the red is the simple model, blue is the actual or more accurate. So what we see in the simple model is that this is a threshold voltage which is 0.5 volts. Up to the threshold voltage, the current predicted by the simple model is 0, as we saw in the equations, and then it starts increasing and it varies. Okay, actually, so what is happening here, okay, this is important. So let me go back. So what we see here is that this is linear. ID versus VG is linear, but what we see here, this is clearly not linear. Okay, think about this. I will not answer this. You think about why this part, in fact. So now it's linear here, up here, but it is not linear very close to VT. You think about it. What I want to talk about is that in the actual MOSFET, current is flowing at VT also. The current is not 0 at VT. In fact, current is flowing even for gate voltages less than VT. So we had seen this when we are in, I think in the first lecture, when we had talked about the physics of the MOSFET and the fact that as the gate voltage starts increasing, first the holes are driven away in an NMOS transistor, and then slowly electrons start gathering at the interface, and as soon as electrons are gathered, current can start flowing. VT is a somewhat artificial definition of the turning on of current, because the inversion layer is present even for less than VT. Now the inversion layer doesn't suddenly form at VT, so that current suddenly starts flowing. Alright, so in an actual transistor, current does flow for gate voltages less than VT, and this is called as sub-threshold current. It is below threshold, the threshold voltage, so it's called a sub-threshold current. So this is important to recognize. We'll of course assume that current does not flow for VG less than VT, but in an actual transistor, it does flow. It is small, but it does flow. It turns out that the current below threshold, I will not derive this varies exponentially with the gate voltage. Right? In fact, this behavior is somewhat like a bipolar transistor. In a bipolar transistor, the collector current varies exponentially with the base emitter voltage. Here, the drain current varies exponentially with the gate source voltage. There is, if one goes deep into the physics of the MOSFET as well as the bipolar, there one would find that the reason for this exponential is in fact the same in both transistors. But we will not look at this. Just be aware that in the subthreshold region, the drain current varies exponentially with the gate source voltage. Okay. Also, it turns out that for short channel transistors, the subthreshold current is larger compared to long channel transistors because of an effect called as drain induced barrier lowering, and it is often referred to as DIBL or DIBL. And this is kind of a pictorial representation of why in a short channel MOSFET, so even with a 0 gate voltage, when one applies a drain voltage, current flows, and it flows because the two depletion regions start merging with each other, and when they start merging, current can flow from the source to the drain. This is kind of like the punch through effect in a bipolar transistor. Alright, so qualitatively just remember that below threshold current varies exponentially with the gate voltage, and below threshold current is larger in shorter channel MOSFETs because of Dibble. That is all I want you to remember from these slides. Okay, so here is a plot, ID versus VG plot, but this time I am plotting log of ID. This is the y-axis is on a logarithmic scale so that it covers a much wider range. So it's covering 10 raised to minus 12 amperes to 1 milliampere. Red is our simple model. So it is the usual quadratic. On a log scale, of course, it looks very different. And it is going to 0, which is basically minus infinity on a log scale, at the threshold voltage. The actual current, of course, does not go to 0. So this part of the plot is a subthreshold current. And as one can see, this is linear. All right. So an exponential variation on a log scale becomes linear. So you see a linear here, and then there is a knee here. The knee is where the threshold voltage occurs, and then it is bending over and it becomes basically a quadratic. I'm sorry, linear. Yeah, quadratic in saturation. So this I am plotting for a triode region with a very small drain voltage. So the current in this region will be linear with gate voltage. All right. Let us see. Okay. This is IDVG. Okay, so this is another effect. So the IDVG in saturation. All right. So we saw the IDVG in saturation. This is a red one, which is a simple model, and we had seen that this is a quadratic. ID varies as the square of VG. Now it turns out that for short channel transistors, the drain current does not vary quadratically with the gate voltage. It actually varies linearly with gate voltage. Or I should say for very short channel MOSFETs, this is linear. This is due to an effect called drift velocity saturation. So let us spend a couple of slides understanding drift velocity saturation. Okay, let us say we have an electron that is sitting inside a semiconductor, and there is no electric field applied. It is just a piece of semiconductor sitting there without any external forces. Now you know that electrons, well, let's say this is a free electron, right? Not the one bound to a silicon atom, but it is moving about freely in the lattice. And you know that electrons in the lattice experience what is called as Brownian motion. So they have a high kinetic energy and they are moving very fast randomly all over the place, such that over a period of time their average motion in any direction is 0. So here is kind of a represent. So let's say at some point in time the electrons is moving, and it's moving very fast. It moves from here to here. It encounters a collision, it changes direction, it goes there, again collision, and keeps doing this. So this is, of course, as you know, is Brownian motion, some random motion. Over a period of time, the electron would be at the same place. Of course, this is very, very simplified. One talks about ensembles and average velocities, and the average velocity of a large number of electrons over a period of time is 0. Now let us say that, okay, so what is the average kinetic energy or the velocity of these electrons? I don't know if you remember. So the average kinetic energy of a particle in an ideal gas, an electron is like an ideal gas, half mv squared, can be written as 3/2 kT. Where half kT is the kinetic energy per dimension, and 3 dimensions gives 3/2 kT. Some of this you would have studied in 11th, 12th. M star is the mass of an electron in a semiconductor or in any material, Just m would be the free electron mass, and again there's a lot of too much physics here, but I'm just saying that this is called an effective mass. So the mass experienced by an electron moving in a lattice is different from the free electron mass, and it's called m star. Okay, that's all. So we can use this equation to find the, so Vth is the thermal velocity, although it is a speed actually. So for some reason physicists have called this a velocity. Anyway, this is the magnitude of the velocity is can be given as square root 3 kt by m star, and it turns out to be 10 raised to 7 centimeters per second for electrons in silicon. Alright, so this is the speed at which electrons are moving in the silicon lattice without any field applied, with nothing. This is just the random Brownian motion. Okay, now let us say we apply a field. So positive here, negative here, an external electric field. So of course the electrons will move from the left to the right. Alright, and the way this happens is that on top of this random Brownian motion, there is an additional velocity component imposed, which we call drift velocity. So again, if you look at this pictorially, what happens is, so let's say the electron is here at some point in time, and it is moving at a very high speed. Because of the electric field, its motion will be slightly, move towards the right, because it is also experiencing an electric field on top of its random motion. Then of course it encounters a collision, it changes direction, but again the slope is different, right? So because of the electric field, it is moving slightly toward the right, and then it keeps doing that all over the place. And again, as I keep saying, this is a pictorial representation. So by the end of that same time period, the electron would have moved from here to here. All right, so that this is the drift, the electron drift. So you can see that in that amount of time the electron moved so much, it moved only very little due to the electric field. What this also means is that the drift velocity of an electron is much smaller than the thermal velocity of an electron. All right, typically speaking. I will come back to this in a minute. Okay. So what is the drift velocity? The drift velocity is given by mu n times E, where mu n is the mobility, E is the electric field. And the electric field, if this is a uniform semiconductor, is simply the voltage applied divided by the length. And I'm putting some typical numbers. We saw that at the interface of MOSFET, the electron mobility is about 200. Let's say the voltage is 2 volts, and let's say L is 10 micrometers. Then the drift velocity is 4 times 10 raised to 5 centimeters per second, which is of course much smaller than the thermal velocity of electrons. All right. Okay, now let's see what happens to this drift velocity as a function of length. So let's say as length is reduced, what happens? So as length is reduced, so this is the same equation. And I'm simplifying terribly. So I'm saying, let's say we have a drain voltage, and this is L is the length of the channel. But for the purpose of this very, very simplistic calculation, I'm assuming that the electric field in the inversion layer is constant. It is not, but this is just an illustration. This is not a model that I am deriving. So we say, okay, 200, let's say Vd is 2 volts, and then we can write this as 4 times 10 raised to 6 divided by L in micrometers, centimeters per second. You can derive this. This is very straightforward. So the question I am asking is, well, what happens as L is reduced from 10 micrometers to 0.1 micrometer? All right, so we just plug in the L and find the drift velocity. So we saw that for 10, this is 4 times 10 raised to 5. If we make L equal to 1, this becomes 4 times 10 raised to 6, right? And increases by a factor of 10 as the length reduces. If L is 0.1, this equation predicts that the drift velocity will become 4 times 10 raised to 7. Now here is where the thermal velocity comes in, and it is a property of ideal gases that the thermal velocity is simply a function of the temperature. And if we are operating this at room temperature, this semiconductor, then the thermal velocity is 10 raised to 7. Whatever electric field we apply, the electron will not move at a velocity higher than the thermal velocity. So as the field increases, although this equation predicts that the drift velocity will be higher, this equation breaks down as the drift velocity approaches the thermal velocity. The drift velocity saturates at the thermal velocity. So the highest velocity at which the electron can move in a semiconductor is a thermal velocity, 10 raised to 7. This is called as drift velocity saturation. So here is a plot. So if we plot the drift velocity as a function of the electric field, at low electric fields, the drift velocity varies linearly, as this equation gives. As the electric field increases, the drift velocity slowly does not increase linearly, it increases less linearly, and eventually it saturates at the thermal velocity, which is also called the saturated drift velocity. VD sat is a term used, VD max here, VD sat at very high electric fields. Alright, what does this mean for our MOSFET? What it means is that as the channel length reduces, you can see 2 volts is a very normal voltage. As the channel length reduces, current will not increase according to, with the drain voltage as predicted by our simple model. Okay, there is another way of looking at this. So what is the mobility in this plot? The mobility is actually the slope of this line. Vd divided by E at small e's, otherwise that slope means the derivative dVd by dE here anywhere. So the mobility, if it is a slope, what we see is a slope is decreasing, which means that the mobility effectively is decreasing as a function of the electric field. As the electric field increases, the mobility does not remain constant. So therefore our model, which we had derived and taken the mobility out of the integral, if you remember, is no longer valid at short channel lengths where the electric fields are high. Alright, that is the conclusion. So what is the if? Okay, so here is a quick derivation, again, very quick. So we say Jn of the equation. So we say Jn is Q mu n and E. And now we say, well, mu n E is the drift velocity. So we write it as Q n V drift. And we say, well, at high electric fields, the drift velocity saturates. And so we say, if we were to write this at high drain voltages and the velocity is saturated, then we write this as Q n V sat. And then we find the current as the integral of the current density as we had done before. So J and W dx. Now we substitute for Jn, and V sat is a constant, so it comes out and we get Qn dx, and Qn dx is simply the inversion layer charge, and we had seen that Qn is Cox into Vgs minus Vt. Roughly, very, again, this is extremely rough. I just want to make a point. So if this is Qn and we substitute that here, when we get Id equal to W Cox V sat Vgs minus Vt. This is the, first of all, the current is saturated. Okay, I forgot to mention this important point here, that if the MOSFET has a short channel, the electric fields will become large. Before pinch off occurs, the velocity will saturate because the electric field is large. And if the velocity saturates, the current saturates. So the drain current in a short channel MOSFET will saturate before pinch off occurs because of velocity saturation. And this is the equation of the current in the velocity saturation regime. So this is the saturated drain current. So now this current is varying linearly with VGS minus VT as opposed to the quadratic we found in saturation for a long channel MOSFET. Alright, so in a short channel MOSFET, the drain current varies linearly with the gate voltage in saturation. Alright, so this is important. So that is what that plot was showing that I showed earlier. Alright, and the current is smaller, of course. It is smaller because linear is always smaller than square law. Okay, okay, I said this already. Yeah. So the actual current, see, as I said, this is a very approximate and very inaccurate derivation. What this is saying is that the drip velocity is saturated throughout the transistor, throughout the channel, which is never the case. The drip velocity saturates only near the drain end. So the actual current in a MOSFET is somewhere between the square law and the linear characteristic. It is neither square nor linear, it's somewhere in between. And I remember I had shown this very big BSIM3 drain current equation that will take care of this actual neither square nor linear characteristics of the drain current in a MOSFET. All right. It also turns out that the mobility of electrons or holes in the inversion layer varies due to the gate voltage. And I'm just going to, this is the only slide I have on this. So very qualitatively what happens is, if we think of the Si-SiO2 interface, all right, the Si-SiO2 interface is never a very perfect interface. There are always, defects along it, and it is not a perfect plane. It is ragged and jagged and all that. So if electrons are moving close to the interface, they will experience many more collisions as they are traveling, and more collisions means lower mobility. All right, and now what happens is, as we apply larger and larger gate voltage, electrons are pulled closer and closer to the interface because of the vertical electric field. And as they are pulled closer, they keep colliding more and more with the defects at the interface, and so therefore the mobility is smaller as the gate voltage increases. All right, that's all I'm going to say about it. Okay, let's look at output characteristics. Okay, so these are the ID VD plots for the kind of the simple model is the red, and the short channel model is the blue. So two things we observe here. One is that the current is smaller, and that is due to drift velocity saturation we already saw. So so you notice the other thing. So by the way, this and this is for the same gate voltage. All right. So what you see is, for the short channel MOSFET, the current is saturating at a drain voltage earlier than it is in a long channel MOSFET, and this is due to drift velocity saturation. So before pinch off occurs, the current has saturated. That is one thing. The other thing is, if you kind of look carefully, so I think this one is a better one. So you see the red one, see the slope of the red one, long channel, slope of the blue one, short channel. The slope of the blue one is higher. All right, so the current in saturation is varying more in a short channel MOSFET. Or in fact, to be more precise, we've seen channel length modulation, right? The current in saturation increases due to channel length modulation. What this is telling us is that channel length modulation is larger in a short channel MOSFET. So let's look at that mathematically. In fact, we'll derive a simple model for the channel length modulation also. Okay, so this is the figure we have seen before. So this is of course for a long channel. So this is pinched off here. So again, we are going to apply that same what we call pinch off here we could think of as a velocity saturation region for a short channel MOSFET. So let's derive an equation for channel length modulation quickly, very quickly. So this is our saturation region drain current. Now, as we know, channel length modulation reduces the channel length. So the effective channel length over which this equation is valid. This equation is valid when there is an inversion layer present, and that inversion layer is present only up to an L prime. So I've shown L prime here. So this is L prime. So 0 to L prime, inversion layer is there. L prime to L, there is no inversion layer. So let's call L prime as L minus delta L. So delta L is the region over which there is no inversion layer. It's pinched off. So we write, so this is actually L prime, this becomes, and so we say this is L minus delta L. And we do some Taylor expansion. So we say 1 over L minus delta L is equal to 1 over, so we take the L out, 1 minus delta L over L, 1 over L, and then 1 over 1 minus X can be approximately written as 1 plus X. If X is small, which we are assuming that delta L over L is small, then we make an approximation that delta L by L can be approximately written as VDS by VA. Right? It's again an approximation. Actually, if you solve two-dimensional Poisson's equations, one finds that delta L varies as the square root of the voltage. But we are looking for a simple equation that we can use to solve circuits. So we are making a lot of approximations to deliberately arrive at a simple equation. So we say, okay, delta L by L is VDS by VA, where VA is a constant. In bipolar terminology, this is called the early voltage, because this effect is similar to the base width modulation of a bipolar transistor. For MOSFETs, the more commonly used model is that 1 over VA is replaced by lambda, another constant. Just one constant here, so it's a 1 plus lambda VDS, and so this we substitute in the MOSFET equation. So what we get is mu1 Cox W by 2L, this, which is the long channel drain current, multiplied by 1 plus lambda VDS. Lambda is called the channel length modulation parameter, and it is given to us because it's a function. It depends on the actual physical structure of the MOSFET. So this equation basically is saying that as VDS increases, the drain current also increases in saturation. Without it, if lambda is 0, the drain current is constant. And therefore, the larger the lambda, the larger will be the variation of the drain current in saturation. All right? Okay. Now let us look at how CLM varies with L. All right, we need to understand the IDVD plot. It turns out that if we make two MOSFETs, if we fabricate two MOSFETs, let's say side by side on the same chip with everything else the same technology, but one has a smaller channel length and one has a larger channel length, then here is what happens. So let's say this is a longer channel length, this is a smaller channel length. The extent of delta L for everything else remaining the same. So let's say we have applied the same VG, same VD. The delta L in both these transistors is the same. All right, this is a property again of the physics of the MOSFET, because the delta L primarily depends on the doping densities of the N plus and the P regions, and because the N plus and P regions are the same in both these two transistors, the delta L is the same in both these two transistors. Alright, so let's see what that does to the channel length modulation effect. 1 second. Okay, so let's say you have two different channel lengths. So we'll say, so this is our previous the intermediate version of the derivation. So let me go back and So we are here. So we say L minus delta L and L into 1 minus delta L by L. So we are using that form. So we say delta L by L1, delta L by L2. Now L2, let us say, is the longer channel length. L1 is the shorter channel length. Alright. So what do we see here? Everything else is the same. So let's say W by Ls are kept the same. So W by L1 is equal to W by L2. Mu and Cox are the same. Vg minus Vt are the same. The only difference between these two equations is that this L1 and this L2 are different. L2 is much larger, which means delta L by L2 is much smaller than delta L by L1. So this is larger. This is smaller. So 1 minus this is much closer to 1 than this. This is much less than 1. If this is much less than 1, ID1 is much greater than, 1 if this was 0. So ID1 is much greater than ID2 for any given delta L if the channel length L1 is shorter. This is the reason why short channel MOSFETs experience a larger variation in the saturation region compared to long channel MOSFETs. Alright. In other words, if we were to convert this to this, then this lambda basically becomes a function of L. Alright. So if L is large, lambda will be small. If L is small, lambda is large, or as L decreases, lambda increases, causing more variation of the drain current in saturation. Okay, this is very, very, very important for analog circuit design, and we'll come back to this in a few lectures. We'll see how this one effect changes the whole way circuits have to be designed in short channel technologies. All right. Okay, next two lectures we'll take a slight digression from the MOSFET physics and MOSFET circuits, and we'll talk about SPICE, the circuit simulator, and we'll talk about MOSFET parameter extraction, and then I'll talk about the first SPICE assignment that you are going to do. And then after these two lectures, we'll get back to MOSFET circuit analysis.